All right, in this video, we're going to talk about suggested homework problems from 3.3. Um, the directions to one of the problems that we're going to do is actually incorrect in the book. I hope it's correct in WebAssign, but I'm going to tell you what the correct directions are when we get to that problem. So pay special attention to problem 61 when we get there. Let's start with number 5 here. 5 says y equals negative x plus 1 squared, and we're just supposed to look at the graph here and tell intervals over which the function is increasing and decreasing. It's increasing on negative infinity to negative 1 and decreasing on negative 1 to infinity. Number 7, similar question, is the graph is y equals x cubed minus 4 minus 3x, and it's increasing, looking at that graph, on negative infinity to negative 2, union 2 to infinity, and it's decreasing between negative 2 and 2. Notice these are open intervals. It's not increasing or decreasing at the minimum or maximum point. So f of x is equal to 1 over x plus 1 quantity squared. That graph is given to me there. It's increasing on negative infinity to negative 1, and then decreasing from negative 1 to infinity. All right, that wraps up that little bit where they give us the graph. Now we're going to have to do some calculus to find the answer. So for number 13, y equals x root 16 minus x squared. I'm going to find the first derivative of this function using the product rule. So derivative of the first part, leave the second part alone, plus derivative of the second part, leaving the first part alone. There's 2 of these square roots in the denominator, and there is the derivative of the inside of the square root in the numerator. And the 2's will cancel here. So y prime is equal to root 16 minus x squared over 1. And I'm going to be making a common denominator of root 16 minus x squared. And this is going to be a minus x squared over root 16 minus x squared. So y prime is 16 minus x squared minus x squared over root 16 minus x squared. Domain here is negative 4 to 4. That's going to be important because my critical numbers that I'm going to find must be within that domain. So 16 minus 2x squared over root 16 minus x squared. So number line here, I'm going to just cut it off at negative 4 and at 4, and the derivative's not defined at negative 4 or 4, so I'm going to make open intervals there when I'm talking about f prime on this first derivative test that I'm about to do. The zeros of the numerator are going to be 2x squared is equal to 16. So if 2x squared is equal to 16, x squared is equal to 8. And that's strange that happened. There we go. That's what happened. 16, and then this is 2x squared is equal to 16, x squared is equal to 8. X is plus or minus root 8, which is plus or minus 2 root 2. So negative 2 root 2 is here, positive 2 root 2 is here. And then we would pick a number that is less than negative 2 root 2 like -3. If you just want to verify that, -2√2 is -2.8 something. So -3 is a good test point. -3 squared is 9. 9 times 2 is 18. 16 minus 18 is a negative number. The square root in the denominator is always positive. A negative divided by a positive is negative, which means that this interval is decreasing. Something between -2√2 and 2√2 would be like 0. So a positive 16 over a positive root 16. Positive divided by a positive is positive, and that makes that interval increasing. And then again, when we look at positive 2 √2 would be 2.8 something. So we're going to choose 3. And so that's going to be 16 minus 18 again. That's a negative over a positive. It's a negative. And decreasing, we'll come up to why we have -2 over √2 later in the assignment there. But that's going to be one of the other things that you're going to want an estimate to find a correct test point. So intervals for increasing and decreasing here will be decreasing on the intervals -4 to -2√2, union 2√2 to 4, and then increasing on the interval -2√2 to 2√2. All right. Now at number 17. Y equals x minus 2 cosine of x, where x is between 0 and 2 pi, not included. So y prime is going to be 1 plus 2 sine x, and I'm going to set that equal to 0. 2 sine x is equal to a -1, and sine x is equal to a -1/2. So 30-degree reference angle, or pi over 6, we want radians here. So pi over 6 beyond pi, since we need to be in quadrant 3, pi plus pi over 6. And second answer is 2 pi minus pi over 6. So first answer is 6 plus 1 is 7 pi over 6. Second answer is 12 minus 1 is 11 pi over 6. 0 to 2 pi, neither end is included. I'm just going to put the numbers in here, not necessarily to scale. I just need to show the intervals and pick something between 0 and 7 pi over 6. It's easy to calculate this derivative. I'm going to choose pi, because sine of pi is 0, so 1 plus 0 is a +1. That means that it's increasing here. Between 7 pi over 6 and 11 pi over 6, I'm going to choose 3 pi over 2. Sine of 3 pi over 2 is -1, so 1 minus 2 is a -1, and we're decreasing here. And I'm going to take the limit here as I approach 2 pi from the left. So I'm getting close to a value that exists here. So sine of 2 pi is 0. 1 plus 0 is a +1. Even though I'm not defined at 2 pi, I can take the limit as I'm getting close to it. I can pick any number in there that I want. Also, I can just look at the unit circle and decide what's going on with the sine values there, that they are less than 1/2, or I'm sorry, greater than -1/2. So they're closer to zero than that. So this number, this product here is going to be a negative number, but it's going to be greater than -1. So closer to zero than that. So this is going to be a positive difference or a positive sum. All right, so increasing from 0 to 7 pi over 6, union 11 pi over 6 to 2 pi, and then decreasing on 7 pi over 6 to 11 pi over 6. Let's look at number 21. F of x is equal to -2x squared plus 4x plus 3. So f prime of x is equal to -4x plus 4. We're going to set that equal to 0. X minus 1 equals 0. X equals to 1. Let's put that on here. Here's 1. And we've got some instructions here that say find the critical numbers for part A, which we just did. Complete the first derivative test for intervals that are increasing and decreasing, which we're about to do. So number less than 1 would be 0 that I put into this complete derivative up here. Don't put it into this one where you've manipulated it. So that's going to be a positive, and that is increasing. And then we have a maybe 2, so -8 plus 4, that's negative, and that's decreasing. That makes sense because this is a parabola that opens down and it's going to increase and then decrease. So we're increasing on -infinity to 1, and then decreasing on 1 to infinity. We have a local max at x equals to 1 because we were increasing and then start decreasing. So that shows me that I'm going to have a high point in the graph there where the slope is 0, that critical number right there. And I plug that back in. F of 1 is equal to -2 plus 4 plus 3. 7 minus 2 is 5. So this turns into the 0.15, which would be my vertex. I could also find the vertex form of the parabola there since it's quadratic, and I would know what the maximum was. All right, let's look now at number 27. F of x is equal to x to the 5th minus 5x over 5. And so I'm going to call this 1/5 of x to the 5th minus 5x. When I take the derivative, I'll leave that 1/5 alone on the outside. 5x to the 4th minus 5. And I'll distribute that 1/5 through to make this x to the 4th minus 1. Let's factor that into a difference of squares. So that's x squared minus 1 times x squared plus 1. And I'll further factor that because the first factor is also a difference of squares. X minus 1, x plus 1, x squared plus 1. So when I set each factor equal to 0, my critical numbers are going to be x is equal to -1 or 1. Let's put those on a number line for part B. -1 and 1. And so we have this factor will always give us something positive. So negative times negative is positive, times positive is positive, and this will be increasing. Negative times positive is negative times positive will stay negative, and that will be decreasing. And then positive times positive times positive will be positive and increasing. So we're increasing on -infinity to -1, union 1 to infinity, and decreasing from -1 to 1. And I have not done anything with the calculator with these. I'll let you do part D with the calculator if you wish. But I just am interested here on doing parts A through C with you. So local max at x equals to -1. And if I find f of -1, that's going to give me -1 plus 5 is 4 over 5. So 4/5. So that turns into -1 4/5. And there's a local min. Local and relative mean the same thing. So if I say local and your book says relative, that's the same thing. 1 minus 5 is a -4, so that's a -4/5. And that is 1 -4/5. All right, 35. 35 says f of x is equal to 2x plus 1 over x, which is 2x plus x to the -1st. So f prime of x is 2 minus x to the -2nd, or 2x squared minus 1 over x squared. X squared equals to 0. That's going to give me 0, which is not the domain of my original. My domain of my original is x can't be 0. So I can't have x equals 0 as a critical number, but it is a vertical asymptote that can cause the behavior of the graph to change, and I need to consider that when I do my first derivative test. So I'm interested first in the zeros of the numerator. 2x squared minus 1 equals 0. 2x squared equals 1. X squared equals 1/2. X equals plus or minus root 1 over 2, plus or minus 1 over root 2, plus or minus root 2 over 2. And this is where you get that number there. So plus or minus 0.707 ... that we're going to need to have an idea where it's at on the number line. So we have 0 that I'm going to show as a dashed line as a vertical asymptote here. And then I have negative root 2 over 2, and I have positive root 2 over 2 over here as my critical numbers. So this is part A for my critical numbers. Don't forget that vertical asymptote when you do part B here. And from -infinity to negative root 2 over 2. So that's going to be a product that's going to be bigger than 1. So this will be positive and increasing. This is a product that will be less than 1, so that's negative and decreasing. This product will be less than 1, so that's negative and decreasing. And then this product is going to be bigger than 1, so that's positive and increasing. And you may want to see that graph there. So 2x plus 1 over x. Graph this just so you can see that we're increasing, then turn and decrease towards the asymptote, then decreasing towards this minimum value, and then increasing. I'll show you with this one how to use the calculator to find the minimum and maximum points that we are trying to verify are there, but this one is going to do you absolutely no good to get the exact values, because you have a irrational number for x, you're going to have an irrational number for y. So you're going to have to do the calculations here. So we have a local max at x is equal to negative root 2 over 2, and f of negative root 2 over 2 is equal to, so 2 times negative root 2 over 2 plus the reciprocal of negative root 2 over 2 is negative root 2 minus 2 over root 2, which is another root 2. So a negative root 2 minus root 2 is minus 2 root 2, negative 2 root 2. We have a local min at x is equal to root 2 over 2. So f of root 2 over 2 similarly is 2 times root 2 over 2 will be root 2 plus 1 over root 2 over 2, which is 2 over root 2, which becomes root 2. So this is 2 root 2. This point is going to be negative root 2 over 2, negative 2 root 2. And this one is going to be root 2 over 2 comma 2 root 2. Second, quit just to show you what 2 root 2 is. So we're looking for y values that are plus or minus 2.828 something, something, something. So when we come here to the graph, second, calculate. Let's calculate that maximum first since it happens to the left. So to the left of it, and then to the right of it, we hit enter, and then we come back somewhere close to it and hit enter. And there's our 0.707 something, something, something that's root 2 over 2. And there's our negative 2.828 something, something, something that's our negative 2 root 2. Similarly, if we have second calc, let's find that minimum that's on the right side over there. So there's something to the left of it. There's something to the right of it. Oops. Start that again. Second calc, minimum. There's something to the left of it. There's something to the right of it. And then it's approximately right there. And there's our positive root 2 over 2 and our positive 2 root 2 approximations for those values. So your calculator is not going to give you exact values for X and Y when you use this feature, which is why you do this last as a check after you've already done the algebra. You don't do this as the only way to get the answer because your calculator is trying to slice up into little pieces and get close enough that it thinks that it has the right answer, and sometimes it's off by a little bit. So that has some to do with the pixels as well, but that's it. So if you go into your window and you want to tell it in the trace step right here that you want to make the get smaller parts for the trace, or you want your delta X for calculation purposes to be smaller, it's going to take it a lot longer to make the calculation. But if you make this number smaller for delta X, you're going to get much better answers for your minimum and maximum points and things like that. But you're also going to take a lot longer to make the calculation. So just as an example, if I came down here and said that I want this to be maybe just as an example, I come back here. Well, we'll do that later, some other time. I want to finish this up. So let's look at 43. Okay, 43 has a little difference in it that we haven't talked about yet. When we do these things, if they contain both sine and cosine, which is why you were assigned this problem. So the derivative of sine is cosine, the derivative of cosine is negative sine. When we set this equal to 0, how are we going to solve it? Normally we can't divide by x's, but we're going to say cosine of x is equal to sine x. And we want to divide by the function that's going to give us tangent. So we divide by cosine here and say 1 is equal to tangent of x. And we haven't really eliminated any x's out of the problem by doing this. We've just rewritten that relationship as the quotient of sine and cosine, which is tangent. We haven't lost any information because we still have the vertical asymptotes of tangent. We still have the zeros of tangent. But the main thing here is that tangent is going to be 1 when sine and cosine are the same, and that hasn't changed. So we are getting the same answers to this. So where is tangent 1? Tangent is 1 in quadrant 1 at pi over 4. And it's also 1 at 5 pi over 4 in quadrant 3. So there's our critical numbers when we are between 0 and 2 pi, which we were told for this problem. X is between 0 and 2 pi. So for part B, we have 0, we have 2 pi, we have pi over 4, and we have 5 pi over 4. So our slopes were going to be between 0 and pi over 4. We're looking at cosine is bigger than sine, so positive and increasing. And the between pi over 4 and 5 pi over 4, I could look at, say, pi over 2, and that cosine is 0, sine is 1, so that's 0 minus 1, that's a negative 1, and decreasing. And between 5 pi over 4 and 2 pi, again, x is bigger than y, cosine is greater than sine. I actually have a negative sign value, so minus a negative would be a positive. So positive plus a positive is positive. That's going to be increasing. And so we're increasing from 0 to pi over 4, union 5 pi over 4 to 2 pi. I need to take a quick look and see if they included the endpoints on this or not. They did not. So, and then decreasing on pi over 4 to 5 pi over 4. So then we have a local max at pi over 4. And we can calculate that f of pi over 4 is sine of pi over 4 is root 2 over 2, plus cosine of pi over 4 is root 2 over 2, so that's root 2, giving us our local maximum at pi over 4 root 2. We have a local min at x equals to 5 pi over 4. So f of 5 pi over 4 is negative root 2 over 2 minus root 2 over 2 is a negative root 2. That gives us an ordered pair of 5 pi over 4 negative root 2. All right, here's the problem with the directions that are wrong in the book. And if you, I hope that they're right on WebAssign again. So let's come on down here. So it says that the graph of f double prime is shown in the figure. That's incorrect. You can see that it's labeled f. This is not f double prime, this is f. And they want you to sketch the graph of the derivative of f. So we want to look at the graph that's given, look at the slopes that are going on there, and graph a function that is the slope of that graph that's shown. So ignore this thing about this already being a second derivative. If you don't know how to do that yet, we'll talk about that in like chapter 4. If they gave you some higher order derivative graph and they wanted you to work your way back, we'll have to know how to do what's called an antiderivative before we can do that. So starting with f here, it looks like our derivatives start off tending towards positive infinity. We're reading left to right here, so it's a vertical line that looks like it's going towards positive infinity, and these slopes are all positive but decreasing and look like they're tending towards 0. I'm not saying that there's a horizontal asymptote over there, just saying the graph is getting flatter and flatter as we go along. So just all that I can tell you is that it looks like we have undefined slope at x equals -4, that I'll put a vertical asymptote there. It looks like the slopes are positive coming from the right. So I'm going to come from positive infinity, and then at, I'm just going to draw this curve that's gradually decreasing and approaching 0. Again, not really a horizontal asymptote there. It's not, but it is. It's for the derivative function because we're going to get closer and closer to 0, but not get there on this graph of this looks like a square root function. So looks like what's going on there. So you're just conceptually supposed to see this as we're going from positive infinity towards 0, and you're kind of going to graph that like it's the like a rational function. That's the probably the best approximation that you can give for that right now. The actual function, if you want to know what f of x is going to be the square root of x plus 4. And you can know that from pre-calculus that that's a square root function that's been shifted 4 to the left. And that means that the derivative function is going to be 2 over root x plus 4, the 1 in the top. And we'll look at what that actually looks like here. 1 divided by 2 times the square root of x plus 4. I'm going to zoom 6. And so you can't see that asymptote very well on the calculator, but you see it gradually decreasing like that. It's not exactly rational because it's got that square root in the denominator, but it has that same kind of shape to it. And that's why it's only on the right-hand side, is because of this restricted domain because of the square root. All right, let's finish up with number 79. Right here. So we have the equation v equals k times r minus lowercase r times r squared. K and capital R are constants. So I'm going to multiply through here and say that this is k, capital R, lowercase r squared, minus k, lowercase r cubed. It's just going to make it easier for me to find the derivative here with respect to r. So dv the little r, just to be clear what I'm differentiating with respect to, is 2k capital R little r minus 3k little r squared. Going to set that equal to 0, and we'll get that 3k. Actually, let's factor first. I see a common factor of k and r. So 2r minus 3 little r is equal to 0. So 2r little r, yes. So k r equals 0, r equals 0, which I'm not interested in the context of this problem, because of little r is the radius of your windpipe and it closes to 0. You can't breathe and you die. That's not going to give me maximum velocity here. Or 2r minus 3r is equal to 0. 3r is equal to 2 big R, and little r is equal to 2/3 big R. That's the one that's going to give me the maximum. I'll prove that with the first derivative test here, though, just to show you that I'm restricted here between 0 and capital R, and I have 2/3 R somewhere in between. So if I pick something that is, R has to be a positive number that is between 0 and capital R, is what I'm saying there. So, and it can include that one. If I pick something here that is a smaller fraction than 2/3, like 1/2, then 2 minus 3/2 is, this is positive and increasing here. And then if I pick something bigger than 2/3, like 3/4, then 2 minus 9/4, it's going to be negative and decreasing. So there's a local maximum at R is equal to 2/3 R, because this was increasing and then decreasing. And we can plug that in and see what it is, but it didn't ask us. It just said what radius will produce the maximum air velocity. It didn't ask us for a formula in terms of k capital R and lowercase r to calculate maximum velocity. So that's it for that problem. That's it for this section. We'll come back next time and talk about section 3.4, suggested homework problems. See you for the next video.